So in this video, we will be solving part 2 here, where we have a problem where a turbine generating power from a flowing fluid and using momentum and kinetic energy balances, we are to show that the maximum power generation, assuming perfect efficiency, occurs when the ratio of the outlet to the inlet velocity is 1/3. So to start off here, I have a little diagram of this turbine, and we have our liquid here flowing in and flowing out. So what we do know is for this turbine here, rho, or the density of the liquid, rho times the cross-sectional area times the velocity of the liquid will equal the mass flow rate. And then we also know for the inlet here, again, rho, the density, times the velocity coming in, times the area also equals the mass flow rate coming in. And then over here for the outlet, again, rho times the velocity coming out, and the area is equal to the mass flow rate out. So one more thing that our problem stated was that it was at perfect efficiency. So basically what that means is that our mass flow rate is equal to our mass flow rate in and our mass flow rate out. Alright, so now what we can look at is our momentum balance, and that's going to start off with derivative of the momentum times the velocity of the system with respect to time is equal to, and it is going to be equal to our mass flow rate in times our velocity, our first velocity, or our velocity in, I guess, technically, plus our mass flow rate out, and then our V2, and then our force. And now we can simplify this as well, and it will end up being, the force will actually end up being negative, and that is because our fluid here is pushing our turbine. If the force is positive, then that means our turbine would be pushing our liquid. So obviously we want the liquid acting on the turbine, so that's why our force will be negative. And then it will just equal V1 minus V2 and then our mass flow rate. But again, we already have our mass flow rate up here as rho SV, so we can substitute that in as well right here as rho SV. So now we can perform a kinetic energy balance, and we're going to start that off by saying that power equal to change in kinetic energy over momentum times our mass flow rate. And then we also know that kinetic energy equals 1/2 mv squared. So now we can plug that in up here, and we end up getting these atoms will cancel. End up getting 1/2 or we can just write it as v1 squared minus v2 squared over 2 times our mass flow rate rho s v. And now we also know that power is equal to negative the force times velocity. And again, we already have an equation for negative f, so we can plug that in here. And we would just end up getting v1 minus v2 rho s v squared. And then now we can set these two equal to each other. And we'll get a lot of stuff to cancel. So rho and s will cancel, one of these will cancel, and then this will cancel with this because we can write this as v1 minus v2 times v1 plus v2. So we'll end up getting a velocity equation here where we have velocity equals v1 plus v2 over 2. So now what we can do is plug this velocity equation back in up here. And I'm going to do that over here. So it'll end up being, again, this is for power equals, we have our v1 squared minus v2 squared over 2, or actually this will be over 4 now. And then we have a rho s times our v1 plus v2. And now what we can do also is combine these like terms. We can kind of switch it up here and we'll have rho s over 4, and then we'll have v1 to the third plus v1 squared v2 minus v2 squared v1 minus v2 to the third. So now what we can do is we're actually going to factor out v1 to the third, and you're going to see why we're doing this in a second. But we're going to end up with ratios of v1 and v2 that will be very friendly. So again, this will v1 to the third, factor out that v1 to the third, it'll just be 1. And then here we'll just have v2 over v1. And then minus, here we'll have v2 squared over v1 squared. And then here we'll have v2 to the third over v1 to the third. So now as you can see, we have these ratios of the outcoming velocity to the incoming velocity. And in our problem, we wanted that ratio r, which is from out, ratio of out to in, or we can say v2 to v1. And we want that r to equal 1/3. So we can put that in here as this would just be r, this would be r squared, this would be r to the third. And then we can take the derivative of this with respect to r and set it equal to 0. And if we do that, we will get 1 plus 2r, or 1 minus 2r minus 3r squared. And then set that equal to 0. And if we factor this out here, we will end up with 1 minus 3r and 1 plus r. Make sure that makes sense here. Yeah, that should be right. And then we'll have the r equals 1/3 and -1. But we can disregard this -1 because that negative ratio would mean that the flow is going backwards, which obviously we do not want. So we do end up with this 1/3 ratio that the problem was asking for.